Building AI models has largely been an exercise in brute force. To make a model smarter, developers throw more parameters at it, expanding the neural network until it can reason through highly complex problems. But crossing the 1 trillion parameter mark introduces a severe physical bottleneck. At that scale, computational friction takes over. Responses become sluggish, memory requirements skyrocket, and the ability to track long sequences of information starts to fracture. Operating massive models requires immense financial resources. Because the server costs are unsustainable, tech companies lock their most capable, massive models behind closed doors, restricting access to tightly controlled environments. This chart illustrates standard open-source parameter counts, hovering in the low billions. But right next to them is a massive spike, reaching 2.8 trillion. This is Kimi K3, the world's first open-source model to reach the 3 trillion parameter class. To keep a 2.8 trillion parameter model from collapsing under its own computational weight, Kimi redesigned the core architecture governing how data moves through the network. When you push massive datasets through incredibly deep neural networks, the sequence of information tends to degrade. The deeper the data goes, the harder it is for the model to maintain a coherent train of thought. Kimi solved this with an architecture called Kimi Delta Attention, or KDA, paired with attention residuals. This structure bypasses data congestion using hybrid linear pathways. It smooths the sequence flow, allowing information to pulse from beginning to end without losing its shape. This uninterrupted flow allows K3 to maintain a native 1 million token context window. It can ingest entire books or massive code repositories in a single prompt and fully retain the sequence. KDA is the reason K3 can process these massive inputs without breaking down, making it possible for the model to handle tasks that require tracking data over very long horizons. Operating a 2.8 trillion parameter model should theoretically require enough computing power to bankrupt a standard developer. This visualization shows a structural framework of 896 distinct expert modules. To manage costs, Kimi uses stable latent mixture of experts. It doesn't activate the entire network. Instead, it efficiently routes the request through only 16 experts, leaving the rest of the grid dark. This extreme sparsity gives K3 roughly 2.5 times the overall scaling efficiency of its predecessor, K2. It converts raw compute into capability rather than wasting it on inactive parameters. Because the sparse architecture saves significant compute, the model dedicates those resources to an internal reasoning process before it generates a response. This is controlled via the Reasoning Effort API feature. K3 defaults to maximum thinking effort, natively working through the logic of a problem before providing an answer. This continuous thought engine allows the model to pause, load custom tools dynamically via system messages, and execute web searches or calculations to verify its own steps mid-process. By combining efficiency with internal deliberation, K3 functions as an active problem-solving engine rather than a reactive word predictor. By automatically caching these large prefixes, K3 removes the need for manual configuration and lowers the cost of running long-horizon engineering tasks. K3's capabilities extend to workflows that require a combination of software engineering and visual reasoning. The model ingests visual feedback, like screenshots from a game engine or front-end interface, using those images to autonomously improve the code. This combination of 2.8 trillion parameter intelligence and a 1 million token memory allows the model to remain grounded in the details of complex, multi-step research projects. Kimi K3 proves that frontier intelligence can be delivered in a hyper-efficient, open-source architecture that remains practical for real-world engineering.